Hello my dear students, today I will be discussing with another formula, Rankine's formula. Before that, I'll just mention you about what is slenderness ratio and what are the limitations of Euler's formula. Slenderness ratio, it is represented by the symbol lambda. It is the ratio of effective length of the column to the minimum radius of gyration of the cross section, that is lambda is equal to L effective divided by R minimum, or it can also be represented by LE divided by K. Okay, this R minimum or K, that is called as radius of gyration. Radius of gyration, that is nothing but it is the square root of moment of inertia. It is the ratio of the moment of inertia to the area. Square root of moment of ratio of moment of inertia to the area. Okay, so you can calculate minimum radius of gyration R minimum, or K is equal to square root of I minimum divided by E. E is cross-sectional area, I is moment of inertia. Since an axially loaded column tends to buckle about the axis of minimum moment of inertia, I minimum, the minimum radius of gyration is used to calculate the slenderness ratio. Okay, and this slenderness ratio doesn't have any units. Okay, LE divided by K or LE divided by R minimum, any formula you can use. And next we will see what are the limitations of Euler's formula. We know now Euler's crippling load, that is P is equal to pi square EI divided by LE square. But now this is LE, that is equal to LE divided by K square, that is I have considered that slenderness ratio here. Okay, and Euler's crippling stress, that is sigma, is equal to, we know that stress is equal to load divided by area. So the load is pi square EI divided by this AA get cancelled, so this becomes pi square E divided by LE whole divided by LE divided by K whole square. Okay, now the crippling stress will be high when the slenderness ratio is small. You should remember all these points. Crippling stress will be high when the slenderness ratio is small. The crippling stress for the column cannot be more than the crushing stress of the column material. Okay, there is a crippling stress also, there is crushing stress also. So the crippling stress for the column cannot be more than the crushing stress of the column material. Then it is thus obvious that Euler's formula will give the value of crippling stress of the column, that means equal to crushing stress of the column material, corresponding to the slenderness ratio. Okay, Euler's formula, it is used for the long columns, and it is used for to find the crippling load. Okay, now if the slenderness ratio is less than 80, the Euler's formula for my-steel column is not valid. Okay, sometimes the columns whose slenderness ratio is more than 80 are known as long columns, and those whose slenderness ratio is less than 80 are known as short columns. So columns can also be divided based on this slenderness ratio. I think I have mentioned this in the last theory class. Okay, if it is more than 80 are also known as long columns. If the slenderness ratio is less than 80 are known as short columns. And also it is thus obvious that Euler's formula holds good only for the long columns. This you should remember. The Euler's crippling load, that is used only for the long columns. Okay, so here, in order to avoid this problem, like Euler's formula gives correct results only for long columns, though this formula is applicable for columns ranging from very long to short ones, yet it does not give reliable results. Okay, so in order to overcome this, Professor Rankine, after a number of experiments, gave the following empirical formula for the columns. What he considered both crushing stress also and crippling, crushing effect also and crippling effect also. Okay, so he derived the equation like 1 divided by PR is equal to 1 divided by P into CS plus 1 divided by P PE, where PR is crippling load by Rankine's formula, and PCS, that is nothing but crushing load. Okay, so crushing load, what is crushing load? We know the stress, right? So load we can write in terms of stress and area, because stress is equal to load divided by area. So load is equal to stress into area. So this PCS is ultimate crushing load for the column, and PE, that is crippling load obtained by the Euler's formula. You know PE is equal to pi square EI divided by LE square. Okay, so this is the Rankine's formula. He derived the equation, and finally he got the Rankine's equation, that is to find the load is sigma Cs into A divided by 1 plus alpha into E divided by K whole square, or this sigma Cs into A, that is nothing but load. So PCS divided by 1 plus alpha into LE divided by K whole square, where PCS, that is nothing but crushing load. You can write sigma Cs into A also. Then this is crushing stress, and this is cross-sectional area. Okay, any formula you can use, either this or this. So here alpha is Rankine's constant. It is usually equal to sigma C divided by pi square E. Okay, and LE, that is equivalent length of the column, L effective, and K is the least radius of gyration. So this LE by K is called as slenderness ratio. Okay, now these are the sum of the values of the crushing stress and Rankine's constant for the various materials. If it is a mild steel, sigma C is equal to 320 MPa and alpha is 1 divided by 7500. Cast iron 550 and 1 divided by 1600, and wrought iron 250 and 1 divided by 9000, timber 40 and 1 divided by 750. If it is not given in the examples, you have to use these values to calculate the Rankine's load. Okay, now let us take one example, how to find the load. Okay, so find the Euler's crippling load for a hollow cylindrical steel column of 30 mm external diameter and 2.5 mm thick. Take length of the column as 2.3 meter and hinged at its both ends. Take E is equal to 205 GPa. Also determine the crippling load by Rankine's formula using constants as 335 MPa and 1 divided by 7500. Here what you have to do, you have to calculate both Euler's crippling load as well as Rankine's crippling load also. What is given here? External diameter is given, that is 38 mm. So thickness is given 2.5. How you can calculate internal diameter? That is capital D minus small dt. Why it is like okay, here that is suppose if you take this cylinder, if it is a cylindrical steel, na? Suppose if you consider like this, and so this is a cylindrical, right? It is hollow cylindrical, so like this it is. So here like this it is. So capital D is given, right? That is equal to 38. That is 38. Capital D is 38, and thickness is given, that is 2.5. So this is 2.5, and this is also 2.5. Here both the side thickness is 2.5. You have to find what is this. What is that? 38 minus 2.5 minus 2.5, that is small d. So 38 minus 2 times of t, that is equal to 33 mm. So if internal diameter is not given, you have to calculate like this: capital D minus small capital D minus 2t. Okay, t is thickness, so that's why you get d. Here it is 33 mm. Then length of the column, that is I is equal L is equal to 2.3 meter. It is given, So convert into millimeter, 2.3 into 10 raised to 3 mm. Then yield stress sigma c, that is given 335 MPa or 335 Newton per millimeter square, and Rankine's constant alpha is equal to 1001 divided by 7500. Now you have to calculate both Euler's crippling load also and Rankine's crippling load also. First let us calculate Euler's crippling load. How you can calculate? If we have that formula, PE is equal to pi square EI divided by LE square. So here I is not given, so you have to calculate I. How you can calculate I? This is hollow cylindrical column. So pi divided by 64 into capital D raised to 4 minus small d raised to 4. So substitute the values of external diameter and internal diameter. So what you'll get? Pi divided by 64 into 38 to the power 4 minus 33 to the power 4. So simplify this, you'll get 14.05 into 10 raised to 3 pi mm4 moment of inertia. Okay, now we have calculated. Then we can use the formula. We know now it is given. The column is hinged at its both the ends. So what is the L effective or effective length of the column? That is equal to L only. Both the ends are hinged. L effective is equal to L. So that is equal to 2.3 meter or 2.3 into 10 raised to 3 millimeters. Okay. Now you can use the formula directly. Euler's crippling load PE is equal to pi square EI divided by LE square. So pi square E is 205 into 10 raised to 3 into I, substitute I value, divided by 2.3 into 10 raised to 3 whole square, LE square. So you get this answer. So that is equal to 16.88 kilonewton or 16.88 into 10 raised to 3 Newton. Now what you have to calculate? You have to find Rankine's crippling load. Here the formula is this is the formula sigma Cs into A divided by 1 plus alpha into Le divided by K whole square. Here sigma C value we have, A value we have means we can calculate A value, and alpha value is given, Le is given, K you have to calculate. How you can calculate K? That is minimum radius of gyration is equal to square root of I divided by A. Okay, so first let us calculate A area, that is equal to, it is a hollow circular section, pi divided by 4 into capital D square minus small d square. So capital D is 38 square minus small d is 33 square. So you get this. Okay, then you find radius of gyration. K is equal to square root of I divided by A. I is already calculated, that is 14.05 into 10 raised to 3 pi divided by 88.75 pi. Pi get cancelled. Simplify this. You get 12.6 mm. 12.6 mm. Okay. Now you can substitute all these values in the Rankine's crippling load formula. PR is equal to sigma Cs into A divided by 1 plus alpha into Le divided by K whole square. That is sigma Cs is 335 into A is this divided by 1 plus alpha is 1 divided by 7500 into Le is 2.3 into 10 raised to 3 divided by K is 12.6 whole square. Simplify this, you get 17.16 kilonewton. Okay, so Euler's crippling load is 16.88 and Rankine's crippling load is 17.16 kilonewton. So like this you can calculate the crippling load by using the formula Euler's and Rankine's. Okay, only here extra thing you have to remember what is the radius of gyration, and so it is little bit difficult to remember, and so this ratio Le divided by K, that is nothing but slenderness ratio. I hope all of you understood. If you have any difficulties we can discuss in the class. Thank you.